All right, today we're tackling one of the biggest questions out there, using some incredible new views from the Euclid Space Telescope to map something that we literally can't see.
So here's the central problem, right? Dark matter, it makes up most of the stuff in the universe, but it doesn't shine, it doesn't cast a shadow, it's totally invisible. So how in the world do you even begin to draw a map of it?
Well, the answer, and this is the beautiful part, isn't in the dark matter itself. It's in how that dark matter affects everything around it. The universe basically leaves us clues, written right into the fabric of space-time and carried across billions of years by light itself.
To find this invisible matter, we have to look for its fingerprint, and that fingerprint is gravity, plain and simple, stamped onto the light traveling from the most distant galaxies.
It all comes back to Einstein's mind-bending idea that anything with mass, a star, a galaxy, or, a giant clump of dark matter, actually warps the space around it. And when light travels through that warped space, its path gets bent. We call this amazing effect gravitational lensing.
What's really cool is that this lensing comes in two different flavors. You've got the really obvious kind, called strong lensing. That's when everything lines up just right and you get these wild, distorted arcs and rings. It's like a cosmic funhouse mirror. But most of the time, the effect is way more subtle. That's weak lensing. It's just a tiny, almost impossible to see stretching of a galaxy's shape. It's not flashy, but it's happening all over the place.
And that subtle effect, weak lensing, that's the secret key to mapping the entire invisible universe. It's not about finding one big, obvious clue. It's about building an airtight case from millions and millions of tiny pieces of evidence.
Think about it like this. If you looked at just one faraway galaxy, its shape tells you basically nothing. Is it naturally a bit stretched out, or is it being lensed? You just can't know because you have no idea what it was supposed to look like in the first place.
But, and this is the genius of it, what happens when you look at millions of galaxies in the same patch of sky? Well, while each one is unique, any dark matter sitting in front of them will pull on them all in a slightly shared direction. All of a sudden, you can detect this faint collective alignment. That whisper becomes a roar of evidence for something massive and invisible that has to be there.
So the whole game plan boils down to 3 steps. First, you have to measure the shapes of billions of galaxies with incredible precision. Then, you use some heavy-duty statistics to find that tiny shared alignment. We call it the shear. And finally, you can work backwards from that pattern to draw a map of all the invisible mass that must be causing it.
And this whole enormous, ambitious project, well, this is exactly what the Euclid Space Telescope was designed and built to do. It's the perfect cosmic cartographer for this job.
And boy, is it delivering. Get this, in its very first quick-look data, just a tiny fraction of its total survey, Euclid reported around 26 million detections. I mean, that's not even the main science data yet. The scale we're working with here is just absolutely staggering.
So what makes Euclid so special? Well, it basically has 3 superpowers. First, a super wide view, so it can scan huge areas of the sky really fast. Second, incredibly sharp vision, so it can measure those tiny shape distortions with pinpoint accuracy. And third, a deep reach. It can measure how far away these galaxies are, which lets us build not just a flat 2D map, but a full 3D map of dark matter as it changes over cosmic time.
Okay, so making a map of invisible stuff is cool, no doubt. But why does it matter so much? Because this map, it's more than just a picture. It's a way to test our entire understanding of how the universe works.
And this is the real power of what Euclid is doing. You see, light takes time to get to us, so when we look at galaxies that are really far away, we're also looking back in time. This map isn't just a snapshot of where dark matter is today. It's like a movie showing us how it all clumped together over billions of years.
See, in the very early universe, matter was spread out almost perfectly smoothly. But over eons, gravity started doing its thing. The slightly denser spots, mostly dark matter, started pulling in more and more stuff, forming this huge, filamentary structure that we call the cosmic web. Measuring exactly how fast that web grew is one of the most fundamental tests we have for our theories about the universe.
And this gets to the absolute heart of it. If Euclid's map shows us that this cosmic web grew faster or slower than our models say it should have, that means something is fundamentally wrong with our physics. It could be that dark energy, that mysterious force pushing the universe apart, is acting weird,
Or, and this is the big one, it could even mean that gravity itself doesn't work the way Einstein told us it does on these massive cosmic scales. The stakes just couldn't be higher.
So what's next on this incredible journey? That first look data from March 2025 was really just the opening act. The next big dates to watch are in 2026. We'll get a wider data set in June, and then the first major science release is slated for October. That's when the really deep science, the first high-precision dark matter maps, will start to roll in.
So, with bent light as its guide, Euclid is out there, right now, drawing the definitive map of our invisible universe. The question for all of us is, will that map confirm the story we've been telling ourselves for decades? Or is it about to reveal that we've been completely lost all along? We are truly on the verge of finding out.